Hello everyone, let's solve the Galois 2019 question 3 together. This is a number theory problem. So we have a positive integer n, and the notation n factorial is used to represent the products of integers from 1 to n. What is the largest positive integer m for which 2 to the power of m is a divisor of 9 factorial? So firstly, we can write 9 factorial in the expanded form, which is equal to 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So we can then count the total number of multiples of 2 in 9 factorial, so we can find the largest positive integer of m. So for 8, we have it is equal to 2 to the power of 3. Here we have one multiple of 2, and this is equal to 2 to the power of 2, so there are two multiples of 2, and here there are one multiple of 2. So we can just write 9 factorial as 2 to the power of 3 times 2 times 2 to the power of 2 times 2 times some irrelevant terms we don't need to care about. So by the exponent laws, am times an is equal to am plus n. We can apply it here, so we have 2 to the 7 minus 2 to the power of 7 times a bunch of irrelevant terms. So for question A, the largest positive integer m is 7 because 2 to the power of 7 can be factored out from this expression. Thus for A, we have the answer m is equal to 7. Nextly, we need to find the smallest value of n for which n factorial is divisible by 7 squared. So to be divisible by 7 squared, n factorial must have at least 2 factors of 7. So because 7 is a prime number, only multiples of 7 are integers that have a factor of 7. So the two smallest positive multiples of 7 are 7 and 14. So that the smallest value of n for which n factorial is divisible by 7 squared is 14. So the answer is 14. Now let's solve the third part C. Explain that why there is no positive integer n for which n factorial is divisible by 7 to the power of 7, but not divisible by 7 to the power of 8. So when I first read this question, I was a bit confused, but basically this question wants us to prove that there is an integer that is divisible by 7 to the power of 7, but not 7 to the power of 8 does not exist. So firstly, we can just list out the first 6 multiples of 7. There are 7, 14, 21, 28, 35, and 42. Each of them contributes to one factor of 7. So up to 42, the 42 factorial is divisible by 7 to the power of 6, but not 7 to the power of 7. So note that 7 is a prime number, so only multiples of 7 can be divisible by 7. So the next multiple of 7 is 49, but 49 is equal to 7 squared, so it will contribute to 2 factors of 7. So 49 squared is divisible by 7 to the power of 8, and it is also divisible by 7 to the power of 7. But the previous number 42 factorial is divisible by 7 to the power of 6, but not 7 to the power of 7. So we know that for each positive integer greater than 49, it is n factorial is divisible by 7 to the power and 8, and possibly other higher powers of 7. For if n is smaller than 49, n squared is divisible by at most 7 to the power of 6. So therefore, there is no positive integer n for which n factorial is divisible by 7 to the power of 7, but not 7 to the power of 8. So this integer does not exist. In part D, we need to show that there's exactly one positive integer n for which n factorial is equal to 2 to the power of a times 3 to the power of b times 5 to the power of c times 7 to the power of d times 11 squared 13 squared times 17 plus 19 plus 23. So it must be a huge number, and a plus b plus c plus d is equal to 45 for some positive integers a, b, c, and d. So firstly, when we look at this number n and its factorial, we can recognize that there are two multiples of 11. So the first two multiples of 11 are 11 and 22. So we know that n must be larger or equal than 22. But there's also two factors of 13, so n must be greater or equal than 26, because the first two factors of 13 are, the first two multiples of 13 are 13 and 26. So there's also one multiple of 17, one multiple of 19, and also one multiple of 23. The next biggest prime number is 29. So, but there is no multiple of 29 in n factorial, so it must be smaller than or equal to 29. So so we know that n must be either 26, 27, or 28. So we can just analyze the factors of 26 factorial first, and if it does not work, we can work up to 27 and 28. So this will be the most efficient. So let's get started and find the factors of 26 factorial. So firstly, we can find the numbers containing number containing a factor of 2, which is basically the even numbers. So, but some of them might have more than one, because, for example, 4 is an even number, but it has two factors of 2. So let's just list them out. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and 26. We can then find the number of factors of 2 in them. Okay. So 2 has 1, 4 has 2, factors of 2, 6 has 1, 8 has 3, 10, 1, 1, 1, and then 16 has 4, 18 has 1, 20 is a multiple of 4, so it has 2. 12 should have 2 as well. 22 has 1, 24 has 3, and 26 has 1. Let's double check if I got it right. 1, 2, 1. Yeah, so we know that 26 has these number of factors of 2, so we can add them up. So there's a total of 23 factors of 2. Nextly, we can find the numbers with a factor of 3. So we can have 3, 6, 9, 12, 15, 18, 21, and 24. We can also find, then let's find the number of factors of 3 in case we have duplicates. So 3 has 1, 6 has 1. 9 has 2 factors of 3, so we should be careful of that. 12 and 15 both have 1. 18 has 2. 21 has 1. And 24 also has 1. So we can add up the total number of factors of 10. So in 26 factorial, b is equal to 10. After 3, let's analyze 5. Of 5. So we have 5, 10, 15, 20, and 25. Then we can just find the number of factors of 5. 5 has 1, 10 has 1, 15 has 1, 20 also has 1, and 25 has 2. So we can add them up, and over here there are 6. Lastly, let's do this procedure one more time and find the total number of factors of 7. We have 7, 14, and 21, and each of them has 1 factor. One, and 1, so the total number is 3. So we can find, because remember that m factorial is defined as 2 times to the power of a, 3 to the power of b, 5 to the power of c, and 7 to the power of d, and a plus b plus c plus d is equal to 45. We can calculate a plus, so for 26 factorial, a plus b plus c plus d is equal to 23 plus 10 plus 6 plus 3, which is equal to 42. So 42 is smaller than 45, so that we know that n is not equal to 26. So because 26 is not right, we can try the next closest value, which is 27 factorial. So that 27 factorial is just equal to 27 times 26 factorial. So we don't need to analyze it again. We can just prime factorize 27, which is equal to 3 to the power of 3. So that over here, we know that b is equal to 10 plus 3, which is equal to 13. And over here, a plus b plus c plus d is equal to 23 because the number of factors of 2 did not change. Because 27 does not have a factor of 2, plus 13 plus 6 plus 3, which is 45, which is just what we wanted. But before we can confirm that our answer is 27, let's just check 20 first in case that it also has a value of 45 when we add a, b, c, and d, so that we do not miss a number. So 28 factorial is equal to 28 times 27 factorial. I should put that in the brackets. So 28 is equal to 2 times 2 times 2 or 2 squared times 7. So now we have a plus b plus c plus d is equal to 25 because we have 2 more factors of 2 plus 13 plus 6. And because we have 1 more factor of 7, it will be plus 4. So 25 plus 13 plus 6 plus 4 is equal to 48, which is not equal to 45. So finally, we know that 27 is the only positive integer for which m factorial is equal to 2 to the a times 3 to the b times 5 to the c times 7 to the d times the other factors, and that a plus b plus c plus d is 45. Thank you so much for learning math with me, and I hope you enjoyed it.